Hello, today I'm starting a new series on GCSE level physics and we'll be looking at speed, velocity, acceleration and the suvat equations. First, let's understand the distinction between speed and velocity. In both cases you can say that they have values, for example 30 miles per hour, or if you use kilometres, 30 kilometres per hour. They're not of course the same thing, but the idea is that you measure speed or velocity in terms of a speed, 30 miles an hour, 30 kilometres per hour. But the difference is that when you've got velocity, you also have to say what direction you're travelling. So you might say it's 30 miles an hour or 30 kilometres an hour north. So the difference between speed and velocity is that speed is just the value, or what we call the magnitude, whereas velocity has both the magnitude, 30 miles an hour, and the direction, north. And that is what distinguishes what are called scalars. So speed is a scalar, and velocity is what's called a vector. Scalars simply have magnitude, vectors have magnitude and direction. Examples of scalar would be temperature, or energy, or mass. None of these things have directions. Whereas vectors would be things like forces. If you have a force, it pushes in a particular direction. Or velocity, as we've seen, or even a thing called displacement. In other words, a distance, but a distance in a particular direction. All of these are vectors. So let's just think about the magnitude of velocity. What is velocity? Well, velocity is simply distance divided by time. 30 miles per hour is a distance, 30 miles, divided by the time, 1 hour. 30 miles in 1 hour is 30 miles an hour. As we shall see, that we tend to use the letter S for distance, don't ask me why. So in fact you would write this as S over t. So as I've said, if the speed or velocity is 30 miles an hour, then that essentially simply equates to a distance of 30 miles divided by a time of 1 hour. And that is essentially the dividing line means per. So 30 miles per hour. Now we use what is called the Système International form of units. This means that we always use the same units, so we never get the wrong values because we're using different units. You can't, for example, mix miles and kilometres. You'll get into terrible state if you do that. So we use a standard, which is called the Système International, the standard form of measurements. And for our purposes, distances are measured not in miles but in metres. Time is measured not in hours but in seconds. And masses, which we'll need to see, are measured in kilograms. There are other units, but these will do us for the time being. So in fact, we shouldn't actually be talking about miles per hour or even kilometres per hour. We should be talking about metres per second. So for example, you will always talk about something like 30 metres per second, and that's the same as 30 metres second to the minus 1. You can have it either way. 30 metres per second or 30 metres second to the minus 1 are one and the same thing. But be a bit careful. That S there, which stands for seconds, is not the same as that S there, which stands for distance. You shouldn't confuse them because they should be fairly obviously distinctive. Now I want us to consider what happens if we increase our speed from, say, 30 metres per second to 40 metres per second. That would be called an acceleration because we're getting faster. We're going from 30 metres a second to a faster speed or velocity of 40 meters per second. What would be the average velocity, which I'm going to call v bar? What would be the average if we go from 30 to 40? And I'm going to assume that we go up in a regular fashion. So we go from 30 to 40 with a constant acceleration. Well, just by inspection, I think you probably would deduce that the average would be 35 meters per second. And how would you get that? Well, you'd actually say that that was the initial speed, 30 meters per second, plus the final speed, 40 meters per second, divided by 2. And that's right. 30 plus 40 is 70, divided by 2 is 35. So as long as the acceleration is steady and that you don't change the amount of acceleration, you can essentially say that the average speed is the initial speed plus the final speed divided by 2. And if we give the initial speed the letter u and the final speed the letter v, then essentially we say that the average speed is u plus v over 2. The initial speed plus the final speed divided by 2. But how far will you travel in that time? Well, if it's the average speed, then the average speed is going to be given by distance over time. We've already said that. That's what speed is. It's distance over time. And that means if you rearrange this formula, you get that distance is equal to average speed times time. We got that simply by multiplying both sides of this equation by t. But if distance is equal to average speed times time, for average speed we can put in this equation here. We can say u plus v over 2 because that is what the average speed is. And all of that is multiplied by t. So now we've got an equation which relates distance with initial speed, final speed and time. And that equation is the first of what we call the suvat equations. So called because each of those 5 letters stands for distance, initial velocity, final velocity, acceleration and time. We are going to derive 4 suvat equations. Each one has 4 of the 5 values. In this case, you can see that we've got distance, initial velocity, final velocity, and time. We don't, in this equation, have acceleration, but in other equations we will. So this is the first of a useful equation, and we'll show how to use them a little later on. But before we go on to other suvat equations, let's first think about a distance-time graph. This is distance in this direction and time travelling in this direction. And supposing I draw a line that represents distance against time, so that you are travelling a certain distance in a certain time. What is velocity? Velocity is distance divided by time. What is the gradient of this slope? The gradient of this slope is distance divided by time. So the gradient of a distance-time chart or graph is the velocity. And I hope you can see that the steeper the gradient, the higher the velocity. For example, that would be a very low velocity because it travels a very small distance in a particular time t. This would be a higher velocity because it travels a further distance but in the same time. And this one that I've already drawn would be an even higher velocity because it travels a further distance in the same time. The steeper the gradient, the higher the velocity. But of course I could draw a different distance time chart showing your journey from home to school. If this is home and this is your school, then your journey in the morning might look something like this, because you change your speed as you're going along, I dare say. When you get to school, you stay there, so you don't change your distance, but of course time passes by as you stay at school, and then at the end of the school day you wander home again, and eventually you arrive at home. Now you'll notice that it's perfectly possible to go out and then stay where you are, where the line is flat, and then come back again. So you can always travel in the outwards direction, and you can always travel in the back direction. But here's a direction you can never travel in. You can never travel on a distance time chart like that, or like this, because that implies that you are travelling backwards in time, and that's not allowed. You can only ever move in time in this direction. So make sure if you're drawing a distance time chart that you're never going backwards in time. You can go backwards and forwards in space, but you can never go backwards in time. So let's look at another distance time chart where we've got different things going on, and we'll try and work out what those things are. So once again, this is the distance and this is the time. And let me just first draw the chart, and then we'll show what it is. I'm putting little dots here to separate the different types of action that are going on, and then we'll talk about what they represent. Well, here is a constant velocity, because we've got a constant gradient here, and a constant gradient is velocity. If it's constant, it means a constant velocity. So we're travelling at a constant velocity in this part of the chart. This part of the chart you'll recognise was the same as when we were at school. It's a flat line. We're not covering any distance, but time is travelling past. So that means we're standing still. We're not actually moving at all. Velocity is 0. This is a curve. What does that mean? It means we're accelerating. Why? Because the initial velocity is quite small. You'll notice that the gradient at the beginning is quite low. Low gradient, low velocity. The gradient when we get to this point here is quite high. High gradient, high velocity. So we went from low velocity to high velocity. That's acceleration. What do we do in this part of the curve here? Well, here we start with a high gradient, which means high velocity, and we end with a low gradient, which means low velocity. If you go from high velocity to low velocity, that is slowing down, or decelerating, or braking, if you like. So this part of the curve is an acceleration. This part of the curve is a deceleration. And finally, we've got a straight line, so that means we've got a constant velocity as we travel this distance. But notice it's in the opposite direction. So we would say that this was a positive velocity because we're going outwards, and this we would say is a negative velocity because we're coming inwards. That's the way you tell the difference in vectors about whether you're going in one direction or the other. Here the velocity is in the outward direction, we'll call that positive. Here the velocity is in the homeward direction, we'll call that negative. But notice, although we're going in the opposite direction spatially, we are still going in this direction in time. Remember, we could never have had a line that looks like that. That would have been, particularly if the direction is like that, that would have been impossible, because it would imply that you were travelling at a constant speed backwards in time, and that is obviously not allowed. So now let's think about that acceleration that we did before. You'll remember we went from 30 meters a second to 40 meters per second. And all I told you before was that we simply changed our speed or our velocity from 30 to 40 meters per second. Now I'm going to give you a piece of additional information. I'm going to say that we made that change in a total of 10 seconds. So it took 10 seconds to go from 30 meters a second to 40 meters a second. What was the actual change in speed? Well, if we go from 30 to 40, the difference or the change is 10 meters per second. So we actually changed our speed by an amount of 10 meters per second. And we did that in a time of 10 seconds. And that defines our acceleration. Acceleration is defined as the change in speed divided by the time it takes you to make that change. So in this case, you've got 10 divided by 10, which is 1, and the units are meters per second, because that's what velocity is, per second. So it's 1 meter per second, which can also be written as 1 meter per second squared, or 1 meter second to the -2. All of those are the same thing, and they are the units of acceleration. So just to remind you, acceleration is the change in speed divided by the time it takes you to make that change. So if we do as we did before and say, let us call 30 meters a second the initial speed u, and 40 meters a second the final speed v, then the acceleration is given as the change in speed, which is v minus u, i.e. 40 minus 30, divided by the time it took, which is t. Repeat that again. Acceleration is the change in speed, v minus u, final speed minus initial speed, divided by the time it took, t. If I multiply both sides of that equation by t, I get a times t equals v minus u, and if I rearrange that, I get that v equals u plus at, simply by taking the u onto that side of the equation and then swapping them over. V equals u plus at is the second of the suvat equations. And which ones have we got here? Well, we've got v, final speed or final velocity, u, initial speed velocity, a, acceleration, t, time. The only one we haven't got in this particular formula is s, the distance. Now, before we proceed with other suvat equations, let's now look at velocity time diagrams. Before we did a distance time diagram, now we're doing a velocity time diagram. These are quite different things. And suppose we have a situation whereby we are increasing velocity as we increase time. That, of course, is the very definition of acceleration. If I draw a line down here, this, if we call this u and we call this v, then this line here is v minus u. In other words, it's the difference between v and u. This line along here is measuring time. Change of velocity divided by time is acceleration. So the slope of this line is acceleration. Remember, in the distance time chart, the slope was velocity. In a velocity time chart, the slope is acceleration. And once again, the narrower or the shallower the slope, the smaller the acceleration, the larger the slope, the greater the acceleration. So let's draw another velocity time chart like we did before. This is velocity, this is time. I'll draw it and then we can analyse what we're looking at. There's the first part, there's the second part, there's the third part, fourth part, and fifth part. What does this mean? This means acceleration, because we're changing velocity with time. That's a constant acceleration because it's a straight line. Here, there is no change of velocity as time goes by. That does not mean we're standing still. It means we're travelling at a constant velocity or a constant speed. The curve means that we are certainly accelerating, but the acceleration itself is increasing because we start off with a very shallow gradient, so we've got a low acceleration, and we finish with a very steep gradient, so we have a very high acceleration. So here we are actually putting our foot down on the accelerator ever harder to change actually the acceleration. At this point, once again, it's a flat line, so we are keeping a constant velocity and time is going by, so that we're not accelerating or decelerating, we're just keeping a constant velocity. And here we are going from a high velocity to a low velocity. It's a straight line, so it's constant, but instead of being an acceleration, this is now a deceleration or braking, because we are going slower. Once again, you'll notice it's impossible to have any line that goes backwards in time. Okay, so now we're ready to go on to the third suvat equation. To do that, I'm going to first remind you of the first of the suvat equations. Distance is equal to initial velocity plus final velocity over 2, all times the time. And I'm also going to remind you of the second suvat equation, v equals u plus at. That was the first, and that's the second, and we've derived both of them earlier in this video. So now let me insert for v equals u plus at, I'm going to put that into this equation here. Instead of v, I'm going to have u plus at. So s is going to equal to, well, here we've got u over 2. And then here we've got v over 2. But for v, I'm going to put u plus at over 2 over 2. All right, just repeat what I did. I said s is u over 2 plus v over 2. So s is u over 2 plus v over 2. But instead of v, I'm going to say u plus at. And they're both over 2. And all of those are multiplied by t, because it's u plus v over t times t. So this is u plus v all over 2 times t. Well, what does that work to? U over 2 plus u over 2 is simply u, plus at over 2 all times t. And that is u times t plus at times t is at squared over 2 is plus a half at squared. And that is the third suvat equation. And this one shows you the distance, the initial velocity, the time, and the acceleration. This particular formula doesn't include v for final velocity. And finally, we'll look at the fourth suvat equation, and we'll start with the second, v equals u plus at, which we've already derived. That's the second suvat equation. And now I want to square it. So v squared equals u plus at all squared. Now you should have done in maths how to do the square of a term like this. I'm not going to explain it, I'll just do it. That will become u squared plus 2uat plus a squared t squared. All right, that is the way you multiply. That is essentially u plus at multiplied by u plus at. And if you do that, you'll get u squared plus 2uat plus a squared t squared. Now watch how I manipulate that. V squared equals u squared, well that's just that equals that, plus I'm now going to take 2a on the outside and put the rest in brackets. Well, if I take 2a out, I'm left with ut. Plus, now if I take 2a out of this, well I can't because there's only one a, so I shall be left with an a over 2 times t squared. because when I multiply 2a by ut, I get 2uat. And when I multiply 2a by at squared over 2, I'm going to get, the 2's will cancel, a times a is a squared, and here's the t squared. But you should recognise that ut plus a half at squared is suvat number 3. That is just distance, s. Consequently, v squared equals u squared plus 2a times this great term here, but that is suvat equation number 3, and that's just distance. So that's s. And that is the fourth and final suvat equation. And this one has got v, the final velocity, u, the initial velocity, a, the acceleration, and s, the distance. This one doesn't include time. So having done all of those, you might ask, what's the point? Well, let's just remind you of the 4 suvat equations. The first is s equals u plus v over 2 times t. The second is v equals u plus at. The third is s equals ut plus a half at squared. And the final one that we just derived, v squared equals u squared plus 2as. And you'll notice that in each case, of the 5 values in the suvat equations, s, u, v, a, t, each one of these equations has got 4 of them. There's always one missing. The thing that's missing here is acceleration. The thing that's missing here is distance. The thing that's missing here is final velocity. And the thing that's missing here is time. You'll notice that initial velocity, the u in suvat, appears in all of them. So how does that help? Well, typically in an exam, you will be given 3 values and asked to find a 4th. And of course, what you need to do is to look and find which of the equations covers the 4 values that you're given. For example, suppose you are told that the initial velocity is 0, that the acceleration is 5 meters per second squared, and that the time is 10 seconds. And you are asked to find the final velocity. So a body starts at rest, 0. It accelerates at the rate of 5 meters per second squared for a time of 10 seconds. What is its final velocity? You've got u, a, t, and v. Which of these 4 equations contains u, a, t, and v? Answer, the second one. V equals u plus at. And it's v that we've actually been asked to find. So you simply substitute in v equals u, which we were told was 0, plus a, which is 5, times t, which is 10. And that gives you that v is equal to 0 plus 50, which of course is simply 50 meters per second. So that's the answer. Typically you'll be given 3 values of the 5 in the suvat, and you'll be asked to find a 4th, and all you've got to do is to pick the suvat equation that will give you the 4 values and enable you to calculate. You may have to do some manipulation with the formulae, but you should be able to calculate the one that you're being asked for by choosing the right suvat equation.